Hello everyone and welcome back to the video lecture series for Calculus 1. Today we are going to be covering the derivatives of logarithmic functions and the derivatives of exponential functions with bases other than e. So we're going to start off with the derivative of the natural log of x, which is the inverse function for the exponential function e to the x. So to show you guys where the derivative for natural log of x comes from, I'm going to write it in terms of its inverse, which we already know how to derive. So now y equals the natural log of x can be written as x equals e to the power y. And what I'm going to do is I'm just going to show you where this derivative comes from by taking the derivative with respect to x of both sides of this equation. So I've got the derivative with respect to x of x equals the derivative with respect to x of e to the y. All right, derivative of x with respect to x is 1. Derivative of e to the y with respect to x requires chain rule since y is a function of x, y equals natural log of x. So what I'm going to do is I'm going to take the derivative of the outside, which is going to be itself with the inside left alone, times the derivative of the inside, derivative of y with respect to x is dy dx. Then I'm going to get dy dx by itself by dividing both sides by e to the y. So I get dy dx equals 1 over e to the y. Well, e to the y, this statement right here says e to the y is equal to x, so I'm going to rewrite this as the derivative is equal to 1 over x. So that was just kind of an explanation as to why the derivative of the natural log of x is equal to 1 over x. And because of the domain of the natural log, because you cannot take the log of 0, and because you cannot take the log of a negative number, if you take the derivative of the natural log of the absolute value of x, the absolute value does not make a difference with the derivatives. So the derivative of the absolute value of x, the derivative of the natural log of the absolute value of x is still 1 over x. The absolute value here does not make a difference. It's mostly just there, especially with compositions, in order to get compositions to happen, because you can only have positive values inside of a logarithm. Also, if you are taking the log of anything other than just x, it does require the chain rule. So if you're taking the natural log of some function u to the x, doesn't matter if there's absolute value bars there or not. If you are taking the derivative of the natural log of another function, that composition is going to require the chain rule. So the outside function will be the natural log and the inside function will be the u to the x. So the derivative of the outside is going to be 1 over the inside left alone. Then you will multiply it by the derivative of the inside. So what we're going to do is we're going to take each of these and we are going to find dy dx. So first of all, there's no parentheses here, but you can put parentheses here. We are taking the derivative of the natural log of 4x. Because we are taking the natural log of anything other than just x, we do need the chain rule. So the outside function is going to be the natural log, and the inside function is going to be 4x. So the derivative of the outside, derivative of the natural log of x is 1 over x. So the derivative of the outside will be 1 over the inside left alone. Then we're going to multiply it by the derivative of the inside. Derivative of 4x is 4, which, yes, this does reduce nicely to 1 over x. However, for this next one here on the bottom left, that's not going to happen. So we have y equals the natural log of the absolute value of secant x. So the only reason that the absolute value bars are there is to get this composition to happen in the first place. Because secant can be negative, in order to have the composition natural log of secant, you need to have the absolute value there so that secant is always positive and the composition can happen with the natural log without any domain issues. So as it's written, this function doesn't have any domain issues and therefore it is differentiable. So what I'm going to do is I am going to take the derivative using the chain rule. So the natural log is the outside function and the secant x is the inside function. And the absolute value bars are not going to make a difference with the chain rule or anything like that. So the derivative of the outside function is going to be 1 over the inside left alone. Then we're going to multiply it by the derivative of the inside. The derivative of secant x is secant x tan x. So when you simplify, secant and secant cancel each other out, leaving you with a derivative of tangent x. Now for this next one over here on the top right, we're taking the derivative of x times the natural log of x. So overall, this is a product, so it is going to require product rule, where x is the first part of the product and natural log of x is the second part of the product. So I'm going to start off with the derivative of the first part of the product. Derivative of x is 1 times the second part of the product left alone. Then plus the first part of the product left alone times derivative of the second part of the product. Derivative of natural log x is 1 over x. Since we're taking the natural log of just x, we do not need the chain rule here. So then after a little bit of simplifying, this simplifies down to the natural log of x plus 1. And then for the last one, we're taking the derivative of y equals the natural log of x squared, which I'm going to put parentheses around that because that x squared is inside the natural log. And we're taking that entire thing and we are dividing it by x squared. Now this is going to require the quotient rule because overall it is a quotient. So natural log of x squared is going to be the top function, x squared is going to be the bottom function. You cannot cancel out the x squareds because this x squared in the numerator is inside of a natural log and this one is not. So you cannot cancel something out that is inside a natural log with something that is not inside a natural log. You will need the chain rule when you take the derivative of the top function. So here we go. We've got the dy dx, the derivative, is going to equal, we're going to start off with the bottom function left alone, x squared, times the derivative of the top. So for the top function, natural log is the outside, and x squared is the inside function. So the derivative of the outside is going to be 1 over the inside left alone. Then we're going to multiply it by the derivative of the inside. Derivative of x squared is 2x. Then we are going to subtract the top function left alone times the derivative of the bottom function. Derivative of x squared is 2x. All over the bottom function, x squared squared. And then we're going to do a whole bunch of simplifying. So x squared and 1 over x squared can cancel each other out. And you will notice that both of these terms on either side of that minus sign have a 2x in them. So I'm going to factor a 2x out of both of these terms. So when I factor a 2x out of both of these terms and put the leftovers in parentheses, I am left with 1 minus the natural log of x squared. And then x squared squared in the denominator can turn into x to the 4th. Then this x here in the numerator can cancel out with one of these x's in the denominator. So in the denominator, we will be left with x cubed, and then that just turns into a 2. And then one of the properties of logarithms says that if you have an exponent inside of a logarithm, you can write it out front as a constant multiple. So I can take this exponent out of the natural log entirely and write it out front as 2 times the natural log of x. And this is actually going to be fully simplified. Now, with exponential functions, we covered these a while ago, specifically the derivative of e to the x. The derivative of e to the x was itself. And I said at the time that this rule is not going to be the same for exponentials of other bases other than e. So now that we have the chain rule, you can now take the derivative of any exponential function of any base, and I'm just going to show you where this derivative rule comes from. So we're going to be taking the derivative of some exponential function b to the x, where b is just whatever the base of the exponential function is. If you rewrite b to the x as e to the power of the natural log of b of x, you can take its derivative using chain rule. So the outside function is going to be the exponential of base e, which the derivative is itself with the inside left alone. Then you're going to multiply it by the derivative of the inside. Natural log of b is a constant, so the derivative of natural log of b of x is the natural log of b. So you get a final derivative of the natural log of b times b to the x. So that was just an explanation of where the derivative of the general exponential function comes from. So the derivative of any base b to the power x is going to be itself b to the x times natural log of the base b. And this will apply to any base that is greater than 0. So it's b to the x times natural log of the original base b. So what we're going to do is we're going to find dy dx for each of these. Remember, if you have anything in your exponent besides just x, it does require the chain rule, where the exponential function of base b would be the outside function, and whatever is in your exponent would be the inside function. So taking a look at this first one, we have the derivative of y equals 4 to the power of 3x. Because the exponent is anything other than just x, this is a composition and it requires chain rule. So the inside function is actually going to be this 3x, and the outside function is going to be the exponential of base 4. So we're going to start with the derivative of the outside function. So the derivative of the outside is going to be itself with the inside left alone, times the natural log of its original base, natural log of 4. Then we're going to multiply it by the derivative of the inside. Derivative of 3x is 3. And this really, realistically, you can't simplify anymore, so that is going to be your final answer. So then for the next one, for y equals 3 to the power x, because this exponent is just x, it does not need the chain rule. So its derivative is going to be itself 3 to the x times the natural log of its original base, so times natural log of 3. And then for this last one, remember, you can rewrite this x over 12 as 1/12 x, so you can write this as 108 times 2 to the power of 1/12 x. Then when you take this derivative, remember, constant multiples, nothing really special happens with them, so you're just going to leave that constant multiple of 108 there. No, you cannot multiply this 108 times 2, because order of operations dictates that exponents come before multiplication. This 2 is part of an exponential function. It is the base of an exponential function, so therefore it cannot be multiplied with just a regular constant multiple 108. So do not multiply those together. But that constant multiple of 108 can just stay there. And then we're going to take the derivative of 2 to the power of 1/12 x. So the outside function is going to be the exponential of base 2. And the inside function is this 1/12 x. So the derivative of the outside is going to be itself with the inside left alone, times the natural log of the base, so times natural log of 2. Then we're going to multiply it by the derivative of the inside, so the derivative of 1/12 x is 1/12. And then, for simplifying, 108 divided by 12 is 9. So you get 9 times natural log of 2 times 2 to the power of x over 12, and realistically, that's simplified enough. Now, I do want to point out, before we get into this next slide, that the rule that you use when you have exponents involved all depends on whether your exponent is a number or if your exponent is a variable. If you have an exponent that is just a number with no variable, it's just a numeric exponent. Numeric exponents are going to use the power rule. So when your exponent is just a number, you're going to move down the power and decrease the power by 1. However, if your exponent is a variable or involves a variable, it is going to require the exponential rule, where the derivative is going to be itself times the natural log of its base. So if you have a variable exponent, then you are going to use the exponential rule. So pay attention to whether your exponent is a number or whether your exponent is a variable. So we're going to find the derivatives of each of these, starting with y equals x to the power pi. Is your exponent a variable or a number? Pi is a number, so this is a numeric exponent, so it is going to use the power rule. So I'm going to move down the power and decrease the power by 1. However, for this next one, for y equals x to the power pi, is your exponent a variable or a number? Your exponent is a variable. Therefore, this is an exponential function of base pi. So its derivative is going to use the exponential rules, and its derivative is going to be itself, pi to the x, times the natural log of the base, the natural log of pi. This last one is a composition, and it is going to require chain rule. The inside function is this x squared plus 4. And your outside function is this outside exponent right here. And is this a variable or a number? E is a number. So your outside function is a numeric exponent. So the derivative of the outside will require power rule. So for the derivative of the outside, we're going to move down the power and decrease the power by 1, leaving the inside alone. Then we're going to just take the derivative of the inside. Derivative of x squared plus 4 is 2x. So pay attention to whether your exponent is a number or whether your exponent involves a variable. They use two completely different rules. So we already went over how to find the derivative of the natural log of x. If you have a logarithm of any other base, its derivative is going to be similar, but it is not going to be just 1 over x. So the derivative being 1 over x just applies to the natural log. If you are taking the derivative of a logarithm of any other base b, again, I'm going to show you where the rule comes from, and then I'm just going to give you the derivative rule. So this is just an explanation of why the derivative of log base b of x comes out the way it does. If you were to write it as x equals b to the power y, which we already know how to derive, we'll take its derivative using a little bit of implicit differentiation. So I'm just going to take the derivative with respect to x of both sides of this equation. So the derivative of x with respect to x is 1. Derivative of b to the y with respect to x requires chain rule. The outside function is the exponential of base b, and the inside function is y itself. So the derivative of the outside is going to be itself b to the y times natural log of b, times derivative of the inside is dy dx. Then I'm going to get dy dx by itself by dividing both sides by b to the y times natural log of b. So I get dy dx equals 1 over b to the y times natural log of b. And according to this equation right here, b to the y is equal to x. So I'm just going to rewrite this as 1 over x times natural log of b. And that is the derivative of the log base b of x. And b is just whatever base of your logarithm. It could be 10, it could be 2, it could be whatever. So if you are taking the log base b of x, it is going to be 1 over x times the natural log of the original base b. All of that is in the denominator. And just like the absolute value bars did not make a difference with the derivative of the natural log of x, it doesn't make a difference with log base b either. So if you're taking the derivative of log base b of the absolute value of x, it is still just 1 over x times natural log of b because of the domain of the logarithm function. Also, just as a reminder, if you see a log with no base, remember that its base is 10. It's a common log. So what we're going to do is we are going to be taking the derivatives of each of these functions, starting with the log base 5 of 2x plus 1. Now, if you are taking the log of anything other than just x, you do need the chain rule. So in this case, we have the log of something other than just x. Therefore, this is a function composition, and therefore this requires the chain rule. So the outside function is going to be this log base 5. And the inside function is going to be this 2x plus 1. So we are going to start with the derivative of the outside function. So this is a log base 5. So the derivative of the outside is going to be 1 over the inside left alone, with parentheses around it, times natural log of the original base, so times natural log of 5. Then we're going to multiply it by the derivative of the inside. Derivative of 2x plus 1 is 2. And this doesn't really simplify much. You could put the 2 in the numerator if you want. So then for the next one, we have n times the log base 2 of n. Overall, this is a product, so it is going to require product rule, where n is the first part of the product, and log base 2 of n is going to be the second part of the product. So the derivative of the first part of the product is 1 times second part of the product left alone. Then we're going to add to it the first part of the product left alone, times derivative of the second part of the product. Now, because we have a log of just n, we do not need chain rule. So the derivative is going to be 1 over n times the natural log of 2. And then, these can cancel each other out, leaving you with log base 2 of n plus 1 over the natural log of 2. And then that is going to be your final answer. Now, logarithms, while they will come up in various contexts and in various applications, and you will be taking their derivatives, logarithms and their derivatives also have another application in another type of differentiation technique called logarithmic differentiation. This is a strategy for taking a derivative of a function that has multiple combinations of powers, products, and quotients. We're talking functions that are a real mess, like triple product rules inside of a quotient rule, and everything's being raised to a power, so there's compositions all over the place. Logarithmic differentiation is really for messes like that, where you have a lot of combinations of powers, products, and quotients. If the function, looks really complicated, what you can do is you can use properties of logarithms to kind of break down the expression into, sums and differences, which are easy to derive. And it'll just basically break down the function into a slightly simpler form, and it'll make taking the derivative a lot easier. You will have to use a lot less chain rule, although some chain rule is inevitable. You will probably get away with not needing quotient rule, and you will probably get away with not needing product rule. Now, I wouldn't recommend this technique for just straight products and quotients, like n times log base 2 of n. By the time you actually go through the logarithmic differentiation process, it will take longer than just using product rule. But if you have, a product of 3 or 4 different functions, it's probably a good idea to break it up with logarithms first. Now, the key is that a logarithm is an operation. So you can't just take the log and, that's it. Whatever you do to one side of an equation, you have to do the exact same thing to the other. So you have to take the log of both sides of the equation in order to keep the equation balanced. And technically, you can take any logarithm of both sides as long as it's the same log, but as we just saw, the derivative of the natural log of x is a lot easier than log base b. So what we're going to do, the first step for logarithmic differentiation is to take the natural log of both sides of the equation. And logarithmic differentiation, there's not going to be a whole lot of calculus involved. You're going to be doing a lot of algebra to simplify the expression inside of the logarithm to make things easier so that you don't have to use product rule. You don't have to use quotient rule. And all of that simplifying depends on these properties of logarithms, which I know that you have learned in previous courses, but if you forgot any of them, take this opportunity to write them down. So the product property of logarithm says that if you have a product inside of a logarithm, you can split it up into the sum of 2 separate logarithms. So the natural log of a times b can be separated into the natural log of a plus the natural log of b. Keep in mind this does not apply to the multiplication of 2 separate logarithms, and this does not apply to addition inside of a logarithm. But if you have a product inside of a log, you can split it up into the addition of 2 separate logs. Then the quotient property of logarithm says that if you have a quotient inside of a logarithm, you can split it up into the subtraction of two separate logs. And since order matters with subtraction, it is natural log of the top minus the natural log of the bottom. So natural log of a over b can be broken down to the natural log of a minus the natural log of b. Keep in mind this does not apply to the quotient of two separate logs, and this does not apply to subtraction inside of a log. But this applies to a quotient inside of a log. And then the power property you already saw in action already, and it doesn't matter what your exponent is, but if there is an exponent of any kind inside of a logarithm, you can take that exponent, move it out front, and write it as a constant multiple. And that also applies to any sort of radical which can be rewritten as a rational exponent. So if you have the natural log of the nth root of a, you can write it as natural log of a to the 1 over n. Then you can just take that constant multiple, write it out front, and write it as a constant multiple. So what we're going to do is we are going to take the derivative of this function here, which is x cubed minus 1 to the power of 4 times the square root of 3x minus 1 all over x squared plus 4. Now, if you were to take the derivative as is, overall it is a quotient, it would need quotient rule. The derivative of the top would require product rule, and for the derivatives of both parts of the products would require chain rule. Now, is that doable? Yeah, that's doable. But I'm going to show you how logarithmic differentiation can be used on a problem like this and how it might make things easier. Now, the first thing that I'm going to do is I'm going to rewrite that square root as an exponent of 1/2 just because I know that we're going to have to do this anyway. So I'm just going to rewrite this as x cubed minus 1 to the 4th times 3x minus 1 to the power of 1/2. Now for its derivative, what we're going to do is we are going to be taking the natural log of both sides of this equation. So now that we've taken the natural log of both sides, remember there is two sides to this equal sign, so throughout most of this process you're going to have this natural log of y over here on the front. And overall, I see that there is a quotient inside of this logarithm. So let's break apart the quotient first by taking the natural log of the top minus the natural log of the bottom. I'm going to be using quotient property. So I'm going to split up this quotient inside of this log as the natural log of the top, x cubed minus 1 to the 4th times 3x minus 1 to the 1/2. Minus the natural log of the bottom, so minus natural log of x squared plus 4. Now, a product inside of a logarithm can be broken up using the product property of logs. So if you have a product inside of a logarithm, you can split it up into the addition of two separate logarithms. So that's exactly what I'm going to do with this product here. I'm going to split this up into the natural log of x cubed minus 1 to the 4th plus the natural log of 3x minus 1 to the power of 1/2 minus. Now for the natural log of x squared plus 4, unfortunately there is no rule for addition or subtraction inside logarithms, so you're kind of stuck with the natural log of x squared plus 4. But that derivative is not going to be anywhere near as bad as it was because now that I've broken this up, now you no longer have to use quotient rule and you no longer have to use product rule. Now some chain rule is inevitable, but let's cut down on the amount of chain rule that we have to use. So this outside exponent here, this is an exponent that is inside of a logarithm. You can take any exponent inside of a log and use the power property to write it out front as a constant multiple. So I'm going to take this exponent of 4 and I'm going to write it in front of the logarithm as a constant multiple. So this will turn into 4 times the natural log of x cubed minus 1. Plus, we're going to do the same thing here. I'm going to take this exponent of 1/2. I'm going to write it out front as a constant multiple. So 1/2 times the natural log of 3x minus 1. And then minus natural log of x squared plus 4. Now, because of this plus sign here, you cannot do the same thing with this exponent of 2. The exponent of 2, because that plus sign's kind of getting in the way, you can't write this out front as a constant multiple. And same here with this exponent of 3. You cannot write this 3 out front as a constant multiple because of this minus sign. So we've used all of the properties of logs that we possibly can, so this is about as broken down as it's going to get. So what I'm going to do is I'm going to be taking the derivative with respect to x of both sides of this equation. Since this was originally an explicitly defined function, y equals something x, our variable of differentiation is clearly x. So I'm going to be taking the derivative with respect to x of both sides of this equation. Now, on the left here, for the derivative of natural log of y with respect to x, natural log of y is not in terms of the same variable we're differentiating with respect to, so this requires chain rule. The outside function is natural log. The inside function is y itself. So the derivative of the outside is going to be 1 over the inside left alone, times derivative of the inside, derivative of y with respect to x is dy dx. So we had to use a little implicit differentiation there, but it wasn't that bad. Then everything else on the right side is all in terms of x, so we are going to have to use some chain rule, but we won't have any dy dx's mixed in here. So I'm going to leave this constant multiple of 4 where it was. And then for the derivative of natural log of x cubed minus 1, this is going to require chain rule, where the natural log is the outside function, and x cubed minus 1 is the inside function. So the derivative of the outside is going to be 1 over the inside left alone, times the derivative of the inside, derivative of x cubed minus 1 is 3x squared. Plus, I'm going to leave the constant multiple of 1/2 where it was, and I'm going to do the same thing to take the derivative of the natural log of 3x minus 1. So the natural log is the outside function, 3x minus 1 is the inside function. So the derivative of the outside is going to be 1 over the inside left alone, times the derivative of the inside, which is 3. Then minus, for the derivative of natural log of x squared plus 4, this is going to require chain rule again, where the natural log is the outside function, and x squared plus 4 is the inside function. So the derivative of the outside is going to be 1 over the inside left alone, times derivative of the inside, which is 2x. Now I'll clean this up a little bit here, and I'll clean this up a little bit mostly with the constants. But remember, with implicit differentiation, you want dy dx by itself. So over here on the left-hand side of the equation, dy dx is being multiplied by 1 over y. So to get dy dx by itself, what I'm going to do is I'm going to take both sides of this equation. Notice I'm using parentheses. And I'm going to multiply both sides by this reciprocal. So I'm going to multiply both sides by y. Whatever you do to one side, you have to do to the other. So 1 over y and y will cancel each other out, leaving you with dy dx by itself. And I'm just going to do a little bit of cleanup here. So 4 times 3 is 12, and I'm going to put the 12 and the x squared in the numerator, and then this x squared minus 1 in the, x cubed minus 1, I can't read my own handwriting, in the denominator. Then plus 1/2 times 3, I'm just going to combine as 3/2, times 1 over 3x minus 1. And then I'm just going to condense this into one fraction, 2x over x squared plus 4. Now this next part's a little bit nitpicky, but if the original function is explicitly defined with y equals something x, and x and y isn't mixed together, the derivative really shouldn't be implicitly defined. So I'm just going to replace this y with the original function. This way the derivative is also explicitly defined. So I'm just going to multiply it by x cubed minus 1 to the 4th times square root of 3x minus 1 all over x squared plus 4. And realistically, this is good enough. This is, as long as dy dx is by itself, that is fine. So this is now going to be your final answer. So that is it for the derivatives of exponentials and logarithms. You can now take the derivative of the exponential function of any base and the derivative of the logarithm of any base. So stay tuned for the next video in which we will be covering the derivatives of our last family of functions, the inverse trig functions. So thank you all very much for watching, and I will see you all in the next video. Bye-bye.